and share screen. All right, section 6. Again, we're wrapping up exponential functions today. Yesterday, we talked about this exponential function, a times b to the x. It will be valuable to know that a represents some starting amount, b represents a constant multiplier. But more specifically, the bulk of our information about our function is going to come from this value, this base of the exponent. All right. And so we talked about growth versus decay. It's kind of the equivalent of a positive versus negative slope for a line linear function. So growth and decay have to do with whether or not the base of the exponent is either bigger than 1 or, for decay, less than 1, right? Because that's a constant multiplier. And if I'm multiplying by something bigger than 1, it's obviously getting bigger. If I'm multiplying by something less than 1, it's getting smaller, growth and decay, right? We're also going to reference these growth and decay functions just so it doesn't like upset you or anything like that. This is the same thing as a times b to the x. We just break up b, this base of the exponent, into a rate of growth or decay. Basically, this is just saying how fast something is growing or how fast something is decaying. We typically describe it with a percentage. You'll see that later in one of the examples that we do. But I want to jump right into the examples so you can see exactly what we're going to be talking about for your test on Tuesday, as well as for this section assignment. Okay, so what kinds of problems are you going to be seeing? So you're going to get several questions that give you a function to graph. Okay, one of those families of questions that you get in algebra classes is graphing based on a given function. And these are pretty simple, by simple, maybe stripped down type of exponential functions. So there's very little information in either of them. But we're going to use that to graph it and show what visually it looks like. So in these questions, it's going to say determine whether the function represents growth or decay. That's going to be a common question to get used to. That's actually a very quick answer. It has to do with the value of the base of the exponent. Is it bigger than or less than 1? That should be a quick answer on all these questions. It doesn't take any work other than comparing a number to 1, right? And I'll deal with that in just a second. And once you've established whether it's growth or decay, then you're going to be graphing it. And so you're going to see these XY tables again. Now, for the record, on my chapter test, I'll make sure I provide you the kind of values that you'll be plugging in for X. So there's no mystery as far like what number should I pull out of the universe to kind of plug into this equation. I will give you some structure to do that. And like any XY table, all that means is that those are the numbers I'm going to be plugging in for X every single time. And then it's just calculator work, all right? And you will be allowed to calculate. So one thing I wanted to point out before I advance this is that both of these problems are in the a times b to the x structure, even though they look a little bit more minimal. And so we're still using a times b to the x, a being some starting amount, or y-intercept in these cases, and b being the constant multiplier. And I just want to translate for you that both of these functions, there is technically an a there, even though it's not written. And so I'll just write both of them with that in mind. Okay, both of these things are true. So technically there is an a there, even though it's not written. Okay? It's multiplying by 1. Okay, and that's fine. But I wanted to make sure I illustrated this because we're going to come into a problem in just a second where we have to be able to identify like what value is here or plug in a value. And so technically in both these cases, that a value, that starting amount is there. It's just that it's starting at 1, whatever that 1 may represent. Okay, could be in money, maybe it's $1. And then my constant multiplier in this case would be 2. So I'm doubling the amount of money I have every time or something. Okay, just as a for instance. In this case, maybe again, it's $1, but now it's getting cut in half every time, right? Again, this represents that constant multiplier, and that's how we're determining growth or decay and rates of growth and decay, how fast it's happening. Okay, but I want to make sure I showed you guys that. And for the record, also, you will come across a couple problems where this is not 1. There's some other number there. And so from an order of operations standpoint, how would I go about solving this problem? Well, according to order of operations, I have to deal with the exponent first. Okay, so as you're working through these problems, make sure that you're doing this calculation first, whatever it may be. Okay, whatever the base of my exponent is raised to whatever power first, and then that result, I'm going to multiply by whatever a is. That's the general order of operations then. Okay, so let's go ahead and jump into these problems. I'm going to show you how to go about graphing them, basically just creating an XY table and describing growth versus decay. So this solution sheet can be found on the Google Classroom as well. Okay, so this is our same question. We're given y equals 2 to the x power, and we're asked to graph it. Well, first we're asked to determine whether it's growth or decay. And so the base of the exponent, that 2, is going to determine whether or not it's growing or decaying. And the simple thing I have to do is compare it to 1. 2 is bigger than 1, therefore it's exponential growth. That should become an automatic as soon as you sit down to any of these problems, being able to identify growth or decay. Just compare it to 1, right? 2 is bigger than 1, that means my constant multiplier is causing it to grow every single time, okay? But now for the interesting part, the XY table. Okay, I gave you this series of values for this example, right? -2 through +2. And basically what we're going to do is evaluate each of these values over and again, which means to say is I'm going to take each of these x values, plug it in for x, do the calculation, see what y equals on the other side of it, right? So in this case, some of these you might be able to do in your head and they're super fast. If you need a calculator, use a calculator, all right? You will be allowed to use a calculator for your test. So if I plug in 2 to the 2 power, or 2 times 2, is 4. What we've just done is created a coordinate point. 2, 4 represents a coordinate point on whatever this will end up looking like, right? Keep going, right? 1 point's not enough to figure it out. So if I plug in 1 now, 2 to the 1 power, or just a single 2 equals 2. We just created another coordinate point, 1, 2, right? And so there's my second coordinate point. Now, with just those two, it might even look just linear, but obviously I got to keep going. So now when I plug in 0, 2 to the 0 power, anything to the 0 power equals 1. So this part is really just a recall back to section 4 on exponents. So make sure you're used to doing this on your calculator and stuff. So now I've created another coordinate point, 0, 1. There's that y-intercept I talked about, right? That starting amount. Technically, there is a 1 in front there for my starting amount. That represents the y-intercept in this case. All right, so now I'm starting to see the curve. And now this is where a lot of students get a little confused, is when I start having to deal with the negative exponent. So I'll just take the time to remind you. My suggestion, when I do -1, 2 to the -1 power, just do the positive power, and then at the very last moment, flip the fraction, because that's what that negative sign is going to do. So if I were to do 2 to the 1 power, and I get 2, well, great. But that negative sign is going to flip that fraction, so that 2 becomes 1/2, or 1/2. 2 to the -2 power, just do 2 to the 2 power, that's 4. But that negative sign is going to flip that fraction, I get 1/4. Okay? And again, what we've just done is we've created a series of coordinate points, and we're going to see that signature boomerang banana type of shape right there, that curve, right? Now, one thing else I want to point out, regarding, you're going to be asked about domain and range, which have to do with possible x values and y values. The spoiler alert there is that all exponential functions, domain is anything. It's all real numbers, okay? There is no limit to what this exponent can be. However negative or however positive, decimals, fractions, doesn't matter, okay? 0 doesn't matter. Where it will get interesting is my range limitations. Now, what you may notice is look at these y values. They get increasingly bigger, and they're just going to start taking off, right? This is going to accelerate up. It's going to go super big, super quick, and there's no limit to how tall or how high this exponential function can go. So it can go off to a positive infinity. Where it's interesting, and you may recall this from the unit that we did last year in Math 1 on exponential functions. But as I go backwards, as I move left, you'll notice that these start getting smaller and smaller. And I'm starting to get smaller fractions. What you'll notice is that I could keep going and the fraction will get smaller and smaller, but it'll never quite touch 0, okay? And what ends up happening is there's like this invisible force field on this x-axis. And this function, no matter how much I were to zoom in and get closer and closer, there would always be a little bit of a gap. Because what's happening is I go this way, is I keep cutting it in half. So 1/4 will become 1/8, 1/8 will become 1/16, 1/32, 1/64, 1/128, okay? Basically, my fraction gets smaller and smaller and smaller, but it's never quite getting to 0. In math, we call this an asymptote. Right? It's a funny word, but basically it means a force field. Okay, it's going to get infinitely close but never quite touch. So for range, in this case, it's going to be all numbers bigger than 0, but not including 0. All right, so let's move on to the next one. In this case, we were given y equals 1/2 to the x. We're going to have the same procedure here, still making the next y table, still dealing with my exponent properties and stuff. But now I see that the base of my exponent is less than 1, which means I'm dealing with decay. So this will have a different look, and we can actually see both of these graphs kind of jumping to the finish line, see how they compare. Reading left to right, a growth function is going to increase. Reading left to right, a decay function is going to decrease. Okay, but back to this problem. So the fact that this was less than 1, 1/2 is less than 1, means that this is a decay function. So my values will get smaller and smaller and smaller as I go, as I increase this direction. But the process is still the same. I'm going to do the same thing with my XY table. I'm going to give a bunch of X values. I'm just going to plug them in and see what happens. All right. So when I plug in 2 and 1/2 to the 2 power, that's 1/2 squared. Same thing as 1/2 times 1/2. That's going to give me 1/4. Okay. The other property we could use here for exponents was that if ever I raise a fraction to an exponent, it's the same thing as saying, so if 1/2 was squared, that's the same thing as saying 1 squared over 2 squared. Well, the 1 squared is 1, 2 squared is 4, 1/4. Okay. To the 1 power, 1/2 to the 1 power, doesn't matter how complicated that base is, that's just going to be itself. Okay. And what we've done is, again, we've created coordinate points. We graph those coordinate points, right? Plug in 0, no matter what that base is, anything to the 0 power is 1. People tend to be pretty comfortable with these positive ones and down to 0. Where it starts to get a little more interesting is with the negative exponents. Okay. Again, what you could do for this, for the negative 1 power, just send 1/2 to the 1 power. That's 1/2. And then the negative will flip the fraction. So 1/2 becomes 2/1 or 2. Negative 2 power, that's the same thing as saying 1/2 to the 2 power. You actually already solved that, which is 1/4. And then the negative tells me I flipped the fraction. So 1/4 becomes 4/1 or just 4. And again, what we've done is we've created a series of coordinate points that when you graph them, you get this curve. Again, there's our invisible force field. Right there, it'll get infinitely close, but never quite touch this x-axis. It'll go infinitely up that way. Okay, all right, let's move on. So next, I'm gonna go through a word problem. A little easier to see on my notebook. Okay, so here we're given a word problem based around exponential functions. And before you get super intimidated by word problems, they all kind of ask the same general question, okay? And they all kind of present the same kind of way to solve it, right? You're gonna be given some information. That's the word problem part. They're just giving it to you in words, basically. Here's some information. Typically, the first question or one of the first questions you're gonna be asked about that information is to create an equation that now I can use that to solve for some unknown, some variable based on the information I'm given. And they'll typically tell you what kind of equation structure you're gonna be plugging into. So really all you have to do is identify like, all right, this 34,109, what value will that be in my equation? That's pretty much what you'll have to do for this first portion, okay? And then once you have the equation, the way that these word problems typically progress is that now I'll be comparing some variables and stuff. So now I'll give you a variable to plug into that equation you just created to find out what it's what happens to the other variable. And then I might give you the reverse of that. And you'll see that progression in this problem. So here we're given some information. This is actually true. I researched this, right? In 2010, Big Bear's population was 34,109. The population has grown by about 1.18% each year since. So the population is increasing. Right? Not by much, but it's increasing. Our job here for part A, and for most word problems, is going to be to write a function. In this case, they tell us it's going to be growth, right? Which makes sense because it's growing by 1.18% each year, right? Write an exponential growth model that represents the population Y t years after 2010. Find Y when t equals 9.5. In other words, we're going to solve for a population 9.5 years after 2010. In other words, about a year ago. okay? So that's the general progression of these kinds of word problems. You will get a couple in your assignment, you'll see, right? And then for part B, we're going to solve for the other variable. Basically, I was given t here. I'm going to plug that value into my equation, and I'm going to find y, which will be some population, some amount of people that live in Big Bear 9.5 years after 2010. In other words, about summer of 2019. I'll use that to figure out how many people lived in Big Bear. Then for part B, now I'm going to estimate the population when, a time when the population was 35,000. In other words, here is the number of people in Big Bear. At what time after 2010 did I reach that number? Okay, for whatever reason. Maybe it was a milestone for something, okay? Anyway, so let's jump to the solution sheet. I'm going to fly through this real quick, and then we'll be done. All right, so there's our problem. And we're asked to write an exponential growth equation. So I'm going to use this model right here. And the reason I chose this as opposed to a times b to the x, technically this is still a times b to the x. B is just broken up into this rate right now. The reason I'm using that is actually because of this fact right here. Percentages. Anytime you see a percentage in an exponential function, it's talking about rate. Because that percentage is representing how much above and beyond is it growing? How fast is something growing or decaying, depending. Okay, and the fact that it's a growth model, in other words, the population's increasing, which is what they told us in there, that's why I'm using 1 plus r. You may recall that there was another equation that had 1 minus r. The minus r represents decay. Okay, so that's the model I'm going to be using. And again, I could have used b, but it doesn't give me the information in terms of the multiplier. It gives me the actual rate of growth. So that will be more convenient for this model. All right, so then it's just to identify the pieces that I need. Y and x are going to stay y and x. Actually, technically, I'm going to use t for x because that's going to represent time. But y and t in this case will stay y and t. Those are my variables. How many people live in Big Bear at a given time versus how long it's been since 2010. Those are variables. A, again, represents some starting amount. In this case, that's the 34,109. So that's going to be my starting amount, the constant population that happened in 2010, right? R is going to be my rate of change. Now, they told me it was 1.18% growth. In order to use that, because I don't have a percent button on my calculator, I need to convert this into a decimal. And in order to do that, I'm going to move that decimal point 2 spaces to the left, okay? Because think about it, if it had 1%, that'd be 0.01. So 1.18% is 0.0118, okay? So that tends to be where a lot of students mess up right there. When I start with the percentage, move the decimal to the left, my number should get smaller. If I start with the decimal, move the decimal to the right to find the percentage. That's how it kind of goes, okay? So now using those 2 pieces of information to plug into here, here's what happens, okay? There's my 34,109, that's my starting population. 1 plus r, the r is that 0.0118, okay? And that 1 for the record represents like, okay, this is just, it's staying the same. The 0.0118 growth represents how much more it's growing. And so that's what it would be. If it were decay, it would just be minus that amount, but we're dealing with growth. And then t is x. That's going to be my time. That's going to be how long it's been since 2010. Well, I can do this calculation very simply. 1 plus 0.0118 is 1.0118, right? So this is technically what they'd be looking for on big ideas. If you left it in this 1 plus form or 1 minus if it were decay, it's going to want this. You can combine that. That's the actual calculation it can do. All right, so there's my function. Great. That's important because now I can start plugging in stuff for either variable and solving for the other. And it's good because the second part of this question says like, all right, now find y, solve for y when t is 9.5, 9.5 years. So I'm going to plug in 9.5 for t. And now in this equation, when I plug in 9.5 for t, order of operations says I have to do the exponent first. Okay, don't feel like you have to do this in your head. This one would be impossible to do in your head, I would think. But so on a calculator, I would do 1.0118 and then raised to the power of, this is the button that we used in section 4, customize the exponent of 9.5. Yes, it's possible to get decimals in the next one. And we get this crazy ass decimal, right? This represents that 1.0118 to the 9.5 power, okay? You can round it, right? And so that's, now that I've done that, now I'm going to multiply it by that starting amount. Okay, so now I multiply that number by the 34,109, and that gives me my population in the summer of 2019, 38,130 people, approximately. That's the estimate based on this function. Okay, that can be used for lots of things. Okay, maybe you were trying to figure out how many t-shirts you need to get people to celebrate an anniversary for Big Bear. That will give you an idea, especially if you're doing it without a census and stuff. Okay, so that's how that's used from that side. That's the more straightforward way to solve these kinds of problems. This one for part B is less straightforward. So here they give us the other variable. Estimate when the population was 35,000. In other words, 35,000 is going to be Y. That is going to be the population that we're searching. What we're solving for is T, or the exponent in this case. What year or how much time passed before I got to 35,000 people. So this is what I would write in there. And this is typically how these word problems will go. Here's one variable, solve for the other. All right, now let me give you the opposite variable, and now you're going to use that to solve it backwards, basically. So in this case, there's the 35,000 people that I want to search the time for. There's my starting amount. That didn't change. There's my growth rate. That didn't change. And now I'm solving for T. But we technically we haven't learned the mathematical function that will reverse this exponent. That's a math 3 concept. But for this, we're going to use guess and check. Okay? So what I could do here is I could just start plugging in numbers for T randomly and do that exponent, then multiply by 34,109, and try and get to 35,000. Okay? That's a long way. What I could also do is I could divide this 34,109 over here because it's multiplying by this. I could divide it, and that would get me to this point. Right now, I could just do 1.0118 to random exponent values until it matches this decimal. Okay, so for instance, I'll do it the longer way right here. If I were to say like, all right, well, let's say 2 years. 2 years after, so I do like 34, not 34. I would start with the base of the exponent, 1.0118. Okay, raised to the 2 power, so that's 2 years. All right. That number I'm going to multiply by 34,109. I want to get close to 35,000. That's pretty dang close. 34,900. 34,900. All right. Well, it's too low, so I need to increase my years. Now let me try 1.0118 to the 3rd power, so it's 3 years now, an additional year. Multiply that times the 34,109, my starting amount. 35,330. Oh, went too high. So now I know it's between 2 years and 3 years. And if you do it enough times, you can start zeroing in on the exact time. Instead of like round to the nearest tenth, you'd find it to be 2.2 years. Okay. About 2 years and just shy of 3 months. Okay. Anyway, that's called the guess and check method. That's a little more time consuming. You won't get many of those kind of problems. I just did that mostly for fun. But let me stop share. And recording.